Section 1. Stars, Galaxies, and the Elements, circa 13.6 to 4.6 billion years ago. The universe was no longer only a hot, expanding sea of particles and radiation. It had cooled. Matter had begun to gather. Gravity had gone to work, and now, across the darkness, the first great structures of the cosmos were rising. Galaxies, vast islands of stars, gas, dust, dark matter, and gravity, forming across the universe like cities of light in an endless night. In the beginning, the universe was far more chaotic than it looks today. Clouds of hydrogen and helium drifted through space. Tiny differences in density, born in the earliest moments of cosmic history, gave gravity something to build on. Where matter was slightly denser, gravity pulled in more matter. Where gravity pulled, structure began to form. Small clumps became larger clumps. Large clumps became protogalaxies. Protogalaxies merged, collided, and grew. Over hundreds of millions of years, the first galaxies matured. Some were small and irregular. Some became spirals. Some became giant elliptical systems. Each one was a vast gravitational kingdom, holding together billions and later trillions of stars. Section 2. The discovery of galaxies. Billions of years later, Edwin Hubble would help humanity understand that these distant smudges of light were not clouds inside our own galaxy, but galaxies themselves. Entire island universes far beyond the Milky Way. This changed humanity's view of reality. The Milky Way was not the whole universe. It was one galaxy among many. The cosmos was larger than we had imagined. And still later, Vera Rubin would reveal something even stranger. Galaxies did not rotate the way visible matter alone said they should. Their outer stars moved too fast. Something invisible was helping hold them together. Dark matter, a hidden mass, an unseen structure, a vast gravitational foundation that shaped galaxies from the beginning. Galaxies were not made only of what we could see. They were built inside halos of invisible matter, and those halos helped determine how cosmic structure grew. Section 3. The Milky Way begins to form. As galaxies assembled across the universe, our own galaxy was beginning to take shape. The Milky Way did not appear all at once. It was assembled over time. Ancient star clusters formed. Smaller protogalactic fragments merged. Gas settled into a growing disk. Old stars gathered in a halo around the galaxy. New stars ignited in its spiral regions. Bit by bit, the Milky Way became a true galaxy, a rotating system of stars, gas, dust, and dark matter. One day, this galaxy would become the home of the sun, the Earth, and humanity. But galaxies alone were not enough. To build planets, oceans, mountains, and life, the universe needed chemistry, and chemistry came from stars. Section 4. How stars are born. A star begins as a cloud. A cold cloud of gas and dust drifts through space. Gravity slowly pulls that cloud inward. As it collapses, its center becomes denser and hotter. Pressure builds. Temperature rises. Then at the core, hydrogen nuclei begin to fuse. A star is born. This is one of the most important events in cosmic history. A star is not simply a ball of fire. It is a self-gravitating sphere of plasma, held together by gravity, powered by nuclear fusion. Gravity pulls inward. Fusion pushes outward. The star lives in the balance between collapse and explosion. Cecilia Payne-Gaposchkin helped reveal what stars truly are. Enormous bodies made mostly of hydrogen and helium, not compositions like Earth, as many once assumed. Her work changed our understanding of stellar physics forever. Section 5. Why stars shine. Stars shine because they are converting mass into energy. Deep inside their cores, hydrogen atoms fuse into helium. In that fusion, a tiny amount of mass is converted into enormous amounts of energy. That energy travels outward through the star and eventually escapes as light and heat. This is how stars live. This is how the night sky shines. But stars are not all the same. Some are small and long-lived. Some are huge and short-lived. Some burn calmly for billions of years. Some race through their fuel in only millions of years. The mass of a star determines its fate. That truth became one of the great revelations of astrophysics. And one of the scientists who helped uncover it was Subrahmanyan Chandrasekhar. He showed that there are limits to what dying stars can become. A star's mass decides whether it ends as a white dwarf, collapses further, or dies in a much more violent way. And violent deaths would become one of the great engines of creation. Stars do not only produce light, they produce the elements. The earliest stars were formed mostly from hydrogen and helium, the simple elements created in the early universe. But inside stars, new elements began to form. Hydrogen fused into helium. Helium fused into carbon. Carbon led to oxygen, then neon, then magnesium, then silicon, then iron. With each stage, stars became cosmic furnaces, creating the building blocks of future worlds. But there is a limit. Iron does not give a star energy when fused the way lighter elements do. Once a massive star builds up an iron core, it approaches disaster. The core can no longer support the weight above it. Gravity wins. The core collapses in a fraction of a second, and then the star explodes. A supernova. Section 7. Supernovae spread creation. A supernova is one of the most powerful events in the universe. Fritz Zwicky and Walter Baade helped define and explain the nature of supernovae, showing that these were not ordinary stellar outbursts, but catastrophic stellar deaths, powerful enough to reshape entire regions of space. A supernova is more than an explosion. It is a release of creation. In the violence of that collapse and blast, the elements forged inside the star are hurled outward into space. Carbon, oxygen, silicon, iron, and many heavier elements are scattered into the galaxy. The calcium that would one day form bones, the iron that would one day flow in blood, the silicon that would one day form rocks and planets, the oxygen that would one day fill atmospheres. All of it came from stars. The universe began mostly with hydrogen and helium, but stars transformed the cosmos into something richer. They turned simplicity into complexity. They turned raw cosmic material into the ingredients of worlds. Section 8. Neutron stars and black holes. Sometimes the death of a star led to something even more extreme. When a very massive star collapsed, its core did not always become a white dwarf. Sometimes it became a neutron star. Sometimes it collapsed even further into a black hole. A neutron star is matter pushed to an unimaginable limit. Protons and electrons are crushed together into neutrons. What remains is a city-sized object with the mass of a star, so dense that a spoonful would outweigh mountains. A black hole is even more extreme. Gravity becomes so intense that space and time are distorted beyond ordinary comprehension. Inside a boundary called the event horizon, not even light can escape. Karl Schwarzschild first found a solution in Einstein's theory that described this possibility. J. Robert Oppenheimer later helped show that collapsing massive stars could truly produce such objects. And Roger Penrose would deepen humanity's understanding of how black holes emerge from gravitational collapse and how they fit into the structure of the universe. These were not just theoretical curiosities. They became part of cosmic evolution. Section 9. The galaxy as a recycling system, black holes grew in galaxies. Neutron stars remained as the ashes of stellar death. Supernova remnants enriched space. The galaxy became a recycling system. Stars were born, stars lived, stars died. There remained seeded new clouds. New clouds formed new stars, and around some of those stars, planets would eventually form from the enriched debris left behind by earlier generations. This is one of the most important truths in all of cosmic history. Planets like Earth could not have formed in the early universe. There were not enough heavy elements. Rocky worlds require more than hydrogen and helium. They require carbon, oxygen, silicon, magnesium, iron, and other heavy materials. Those materials had to be made first. The first stars made them, later stars spread them, and later generations of stars were born from that enriched material. The universe had to live through many stellar generations before worlds like ours became possible. Section 10. Dark matter and dark energy. As this long process unfolded, galaxies continued evolving. Stars orbited galactic centers. Gas drifted through spiral arms. Black holes grew in galactic cores. Clusters of galaxies gathered under gravity. Dark matter continued shaping the large-scale structure of the cosmos, silently influencing the arrangement of visible matter. And on the largest scales of all, the universe itself continued expanding. For a long time, scientists expected gravity to slow that expansion down. But much later, Saul Perlmutter, Brian Schmidt, and Adam Ries helped reveal a shocking truth. The expansion of the universe is accelerating. Something is pushing space apart. Dark energy. Just as dark matter shaped galaxies through hidden gravity, dark energy became part of the story of cosmic destiny, influencing the future of the universe itself. Even as stars and galaxies formed, the fabric of the cosmos was still changing on the largest scale. Section 11. The birth material of the solar system. By now, billions of years had passed since the hot, dense beginning. The Milky Way had continued assembling. Clouds inside it had become increasingly rich in heavy elements from long-dead stars. Somewhere in one region of a spiral arm, a molecular cloud began to collapse. This cloud was no longer made only of ancient hydrogen and helium. It carried the chemical inheritance of countless dead stars. It carried carbon from stellar cores, oxygen from supernova blasts, silicon from cosmic furnaces, iron from ancient explosions. It carried the history of stellar death inside the material of future creation. From that cloud, around 4.6 billion years ago, a new star began to form. Our Sun. Around it, a disk of gas and dust spread outward. Within that disk, particles collided and stuck together. Dust became grains. Grains became rocks. Rocks became planetesimals. Planetesimals became protoplanets. And the raw material forged by ancient stars began assembling into a solar system. Section 12. Why this age matters. This was the true significance of stars, galaxies, and the elements. Galaxies gave the universe structure. Stars gave it light and energy. Supernovae gave it chemistry. Neutron stars and black holes revealed the extremes of gravity. Dark matter shaped cosmic architecture. Dark energy influenced cosmic expansion. And together, these processes turned a simple early universe into a universe capable of building worlds. The story of stars is not only the story of the sky, it is the story of us. Every atom heavier than helium in the human body came from stellar processes. The carbon in our cells, the oxygen we breathe, the calcium in our bones, the iron in our blood. All of it was forged in stars or created in the explosive deaths of stars. We are not separate from cosmic history. We are one of its outcomes. Section 13. Born from starlight, the galaxies formed, the stars lived and died, the elements were created, and from those elements, one day, would come oceans, continents, life, memory, and minds capable of looking back into the night and understanding that they, too, were born from starlight. This was the age when the universe learned how to build, not just light, not just structure, but the ingredients of everything that would come next. The stars lit the cosmos, the galaxies organized it, and the elements made the future possible.